Alright, this section represents the beginning of a more powerful use of the infinite series that we used before. Before I do anything, I want to remind you of something. Consider, if you will, consider the function f of x equals a sine of x. Now, we're going to be doing some graphing and things like this, so if you're following along, make sure your calculator is in radian measure. Alright, what I want to do is first construct what's called the linearization of sine of x at a certain point. So first, compute the tangent line to f of x at x equal to 0. So you remember, it does something like this. You have sine of x goes like this, and I don't need a lot because I'm focusing around 0. So just around here. And if I try to find the tangent line here, it's a pretty flat looking line. But this is my tangent line. If you remember, the way to get this is first we need the slope. So the slope, m, was equal to the derivative at that x value. So it's equal to f prime of 0. Well, to get that, then, f of x equals, f of x equals sine of x. So f prime of x equals cosine of x. And so m equals f prime of 0, that's cosine of 0, and that equals 1. Now the point here that it's going through is 0, 0. So the tangent line then goes like this. It goes y minus 0 equals m times x minus 0. This here is the y value of the point, and this here is the x value of the point. I found m to be 1, so I have y equals 1 times x. That's it. Just y equals x. Or y equals x. Now, to facilitate what we're going to do, I would typically do graphs on your calculator, but the pixels are so limited in nature that I'm going to use a more powerful graphing program to do it. And I'll remind you of what that is. It's a free download should you want to pursue it, and it's called Geogebra. And it is a very powerful program, and the graphs look really nice. What I'm going to do, I'll start here with f of x equals sine of x. Okay, here I've graphed sine of x. Here you have the curved part is sine of x. So f of x equals sine of x is the curved part. And then y equals x is the straight line. One thing I'm going to do, I'm going to start keeping track of these things with a different notation than y. I'm going to use the following phrase. I'm going to call it p sub 1 of x. And the reason I'm doing that is the 1 matches the degree of this particular polynomial, if you will. It's a first degree polynomial. But The important thing is this, right around 0, that's where I found the tangent line at 0. This portion of the graph, look how close the line is, almost exactly the same as f of x around x equals 0. Look at that. You can see just by looking at this that these two are not far off from each other. I mean, they start to deviate once you get outside this little oval I've drawn, but I would say somewhere to negative 0.4 to maybe 0.4, there would be no problem in using this as a way of estimating sine of x. So if I wanted to estimate let's say sine of 0.2, I could use P1 of x equal to x. And that's really easy to do. P1 of 0.2 is approximately equal to 0.2. Actually, I don't mean that P1 of 0.2 actually equals exactly 0.2, but that is approximately sine of 0.2. I'll show you how close they are. If I use a calculator to do this, sine of 0.2 gives me 0.198, and that's not very off from 0.2. The difference is very small compared to the two of them. So it would be so easy to estimate from negative 0.4 to 4 using P1 of x instead of x. You may remember P1 of x equals x is called the linearization to f of x at x equal to 0. And we have that P of x, P1 of x, simply equals x. The coefficient is 1, and there is no constant term. Now what we're going to try to do is come up with higher things than besides linearization and try to estimate sine of x even better than just this. In fact, we're going to try to get it more exact and more exact as we go. So the linearization is a line. This line happens to be the tangent line to sine of x at the origin. Next, we want a quadratic approximation to f of x equals a sine of x at x equal to 0. So the way we set this up is I'm going to call it P sub 2. And what you do is you leave the line part of it alone, and what you're going to add to it is a quadratic term. I'm going to say C times x minus 0 squared. The reason why I say x minus 0 because it'll be at that particular value. And in fact, there's a little more here than this. I should probably have put a 0 or plus 0 at the end to indicate the constant is 0, but that's not that big a deal. So this is a quadratic approximation. I have to figure out what C is. How do we do something like that? Well, what we do is make sure that P2 double prime of x, actually not at x, but at 0, equals the second derivative of the original function at 0 again. So I'll go back to f of x, that equals sine of x, f prime of x equals cosine of x, and f double prime of x equals negative sine of x. And so f double prime of 0 equals negative sine of 0, which equals 0. So my p2 of x equals x plus 0x squared. Unfortunately, that is the same thing as the original one because of this 0. So I'm not going to improve my accuracy by going to the second derivative. So I'll get nothing better by going to a second derivative than this. However, so unfortunately, this is the same as P1 of x. Let's move on. Cubic approximation. Here's what we want to make sure. We want to make sure that it's a P3 of x, and that will equal the linearization plus the quadraticization, I guess you could call it. And then I want a new constant times x minus 0 cubed. Well, here's what I want. I want p of 0 to equal 0. I want p prime of 0, this are all sub 3's, to equal f prime of 0. I want p sub 3 double prime of 0 to equal f double prime of 0, which I've taken care of all those things so far. But now the big one. I need p triple prime of 0 to also equal f triple prime of 0. So the reason why you do all this is you meet up at the point, but then these other rules, these derivatives being equal, will force the curve to the approximation curve, in this case a cube, to hug sine of x right around the origin. Watch what I mean. If I take this, the third derivative, where was my second derivative at? F double prime of x was negative sine of x. So f triple prime of x equals negative cosine of x. So f triple prime of x of 0 equals negative cosine of 0, which equals negative 1. So then, if I force my my p triple prime of 0 to be that, let me take the third derivative of this. So if I take the first derivative, this becomes 1. That doesn't even count anymore. And now this, remember, is just c times x cubed, so you'll get 3cx squared. Let me take another derivative. P sub 3 double prime of x equals, now this time the 1 will go away because of the derivative, but this will become 6cx. And then p sub 3 triple prime of x equals 6c. And I already know that f triple prime of 0 equals negative 1. So I need p sub 3 triple prime of 0 to equal f triple prime of 0. And so I have negative 1 equals 6c. In this way, I'm able to figure out the constant. I get negative 1/6 equals c. And so my p sub 3 of x looks like this. I'll have the original linear one, then I'll have this quadratic one, which didn't do anything for us, but now I have a real c. Or, more simply, now what I'm going to do is graph this thing and sine of x on the same graph and see how they compare. Now take a look at this. This is even closer than before. Right here, this curve that is going out like this is f of x equals sine of x, and then this down here is p sub 3 of x equals x minus 1/6 x cubed. You can see now it's even better on a better approximation. It looks like it goes farther and farther than before. Let's take a look and see how they do at 0.2 like I did before. So I already had that f of 0.2 was equal to 0.19867. Now let me throw in that number for p sub 3. And these are not exact, these are approximate. Now look at this. This agrees with sine at 5 places of decimal accuracy. So you can see this is a lot better. And I can go on. I can go into fourth power, then a fifth power, then a sixth power, as far as I need to go to get the accuracy that I want. Why is this such a great deal? Because computers deal with polynomials, and so do mathematicians, way better than things like this. Polynomials are the ultimate in differentiable functions. They have derivatives until you take derivatives of enough derivatives to make them disappear. So, but they're differentiable everywhere. They're differentiable from negative infinity to infinity. They're continuous. There's no good mathematical quality that polynomials do not seem to have. And it's very easy to plug numbers in and get a value. So right now, probably it looks to me like if I go all the way from 1, x equals 1, to x equals negative 1, it looks like my answers are going to be almost exact. Let's test that out a little bit. Sine of 1 is approximately equal to P3 of 1 happens to equal 5/6, but that's approximately 0.8, and I believe the 3's gone, or is it 8/1? That equals 0.83 with a bar over it. So here you see where they're starting to separate from each other. So maybe a little bit less than that would be better. Maybe if I'd go from negative 0.8 to 0.8. But the point is, as I take and get more powers of x involved, I'll get a better approximation for sine of x. So that's what the game's going to be about. This you could think of as a cubic approximation. That's why I have a sub 3. If I did a quartic or fourth degree polynomial, I have p sub 4. Well, these polynomials that I'm using are Taylor polynomials. So the p sub nx's are Taylor polynomials. Here I want to compute the fourth order or degree polynomial to f of x equals ln of x for x values near a equals 1 up. Here we do y minus, if a is equal to 1, this is near a equal to 1, then what we do is we want to have y minus, I don't know what you call it, let's call it y sub 0 equals m times x minus a. So this will be m times x minus 1. But here, this will be y minus f of 1. But f of 1 is equal to 0. So y equals m times x minus 1. Then when I take the derivative, y prime equals just m. But I know that y prime, when I evaluate it at 1, that must equal f prime of 1. Well, f prime of 1, f prime of x is 1 over x. So when I plug in 1, I'll get 1 over 1, and that'll be y prime of 1. Well, this is equal to the slope. So I now know that m is 1. So I get y equals 1 times x minus 1. Or, since this is the first approximation, p sub 1x equals x minus 1. Now let me move on. Now when I go on to the next one, p sub 2 of x, the way I'm going to work it is this. I'm going to keep my original, the linear part, but then I'm going to add on a second portion like this. Since we're around x equal to 1, we're going to add the term x minus 1. It's kind of like you're trying to do a quadratic the way you would do the point slope formula, except this is sort of like a point slope formula. But we can see that p sub 2 of 1 will zero out, which is exactly what I want. So p sub 2 of 1 should equal 0. It should be the original function. And if I plug in 1, I'll get 0 here and 0 here. No problem, that's going to be true. P sub 2 prime of 1 is supposed to equal f prime of 1. And we already know that that's 1. Well, if I take the derivative, p sub 2 prime of x, I'll get, this part will be 1, plus, and then I'll get 2c times x minus 1. Now, unfortunately, when I plug in 1, I will get the 1 just like it says. But this doesn't help me figure out the value of c. To get that, I need a second derivative. So p sub 2 double prime of 1 needs to equal f double prime of 1. Well, the second derivative of ln of x, the first derivative was 1 over x. The second derivative is negative 1 over x squared. So I'll get negative 1 over 1 squared, which will be negative 1. So when I take the second derivative here, this 1 will go away and I'll be left with just 2c. But from over here, 2c has to equal negative 1. So c equals negative 1 half. So that gives my p sub 2 of x will equal the x minus 1 minus 1 half times x minus 1 squared. Moving on. For P3, we need P sub 3 of 1 has to equal 1. And I think what I'm going to do is write what its basic structure looks like. So P sub 3 of x is going to be x minus 1 minus 1 half times x minus 1 squared. And then we're going to have the cubic part. So I'm going to reset my c and do that with it. So I have to go through the same things. P3 of 1 equals 1. And when equals 0. Because that's f of 1. So when I plug in 1, I'll get 0 here, 0 here, and 0 here. Got it, no problem. Then p sub 3 prime of 1 has to equal f prime of 1. And we already know that's 1 over 1. So let's see if that actually works out. P prime of 1, when I take the derivative, p sub 3 prime of x, well, this portion will become 1. This part here, the 2, will come down and cancel the 1 half, and you'll get minus x minus 1. And then the 3 will come down there, plus 3c times x minus 1 squared. Now, if I plug in 1, p sub 3 of 1 prime has got to equal f prime of 1. And we already know that f prime of 1 is 1. So let's see what happens. When I plug in x equal to 1, this goes away and this goes away, and I'll get 1. So far, so good. Then when I take the next derivative, p sub 3 double prime of x, I'll get this part right here will become negative 1. But then here, the 2 will come down, and you'll get 6c times x minus 1. And so p sub 3 double prime of 1 has to equal f double prime of 1. And we already know that to be negative 1. So if I plug in 1, p sub 3, and imagine x is equal to 1, this part will disappear and you'll get the negative 1 just like it says. When I take the third derivative of p sub 3, I'll end up with 6c, and the third derivative here, that's supposed to equal the third derivative of f. The derivative, I probably should keep track of these things here. I have f double prime of x, f prime, let's just do prime of x, is 1 over x. F double prime of x equals negative 1 over x squared. And then f triple prime of x. Imagine this is negative x to the negative 2. The negative 2 will come down front and become a positive 2, and then x to the negative 3. This is the format I'm going to do the derivatives from now on. So when I throw these things in, f triple prime is going to equal 2 times 1 to the negative 3, which will equal 2. But according to this then, 6c, because when I plug in 1, I'm going to need 6c. Let's go ahead and put this stuff in. 6c will equal, I don't know why I put that, will equal 2, or c, equals 1/3. So p sub 3 of x takes the form x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed. Finally, we get to p sub 4 of x. Now, so I can take just the fourth derivative. I already know what's going to happen in the earlier derivatives. So p sub 4 of x is going to look like this. P sub 4 of x is going to equal the p sub 3 of x plus another term. This time it'll be x minus 1 to the fourth. I'll do the same thing as before. P sub 4 prime. I don't need to actually calculate all the derivatives beforehand, but I do have to get to 4 somehow. The only way to do that is take the derivatives, although I'm not going to plug anything in until I get to the fourth derivative. The reason why is because I got no new information here except when I went to the third derivative. The other derivatives, they gave me stuff I already know. So, take the first derivative, I'll get 1 minus x minus 1 plus x minus 1 squared plus 4c times x minus 1 cubed. Let's do it again. P sub 4 prime prime of x will equal, that 1 will go away, this will become negative 1. This will become 2 times x minus 1, and this will become 12c times x minus 1 squared. Take the next derivative, p sub 4 triple prime of x. Now the negative 1 will cancel, and you'll get 2 plus, and then the 2 will come down here and give you 24. And then finally, I'm going to take the fourth root of it, fourth derivative, and that's going to equal 24c. However, that also has to equal the fourth derivative of f. Where is that guy? Right here. The fourth derivative then will be negative 6x to the negative 4. So when I make sure that these two things are equal to each other, that means p sub 4, the fourth derivative evaluated at 1, has got to equal the fourth derivative of the original function evaluated at 1. Well, when I plug in x here, I'll get negative 6. But over here, I'll get 24c. I'll divide by 24 to get c equals negative 1/4. So p sub 4 of x will equal, there was p1, plus, actually I think it was a negative 1/2. It was negative 1/2 minus 1/2 x minus 1 squared plus 1/3 x minus 1 to the third minus 1/4 times x minus 1 to the fourth. You could probably see a pattern already here. I could just start plugging in all sorts of things like this. I see how I could do a fifth, then a sixth, then a seventh. and I can see how we get an alternating type of series. What I want to do is I would like to graph p sub 4 of x together with ln of x. So let's graph p sub 4 of x and f of x together around a equals 1. Okay, here's what we have. This guy right here, that's p sub 4 of x, and this guy right here is f of x equals ln of x. You can see that these things look pretty good, pretty close to each other. Let me take a circle. Let me kind of circle here and see where they kind of are close to each other. You can see the graphs seem almost identical around x equal to 1, or a equal to 1 is the letter that we're using for this notation. So it looks like I can maybe go all the way almost to 1.6, and I could drop back to almost 0.4 and get some accuracy. So let's test the two of them at 1.4. So f of 1.4 versus p sub 4 of 1.4. So you can see they're pretty good to 2 decimal places, maybe not 3, but to 2. And so I just need more to go out, more terms to get what I want. Well, hopefully you could see, so I want you to make some observations here while we did all this stuff. When I went and got, let's go back to P2 for a minute. When I did P2, and I had P double prime of 1, that needed to be F double prime of 1, I got -1 for that. I set 2c equal to -1. This 2 came out as taking derivatives. Now look at the next one. When I get to the P3, right here, this is the guy I'm looking for. Right there, 6c. How did that 6 arise? Remember, I set 6c equal to 2. How did that 6 arise? Well, 6 was equal to 2 times 3 because I took the next derivative from the first. So I originally had the 3 from taking the first derivative, then taking the second derivative made that into a 6. So 6 was 2 times 3. Look at the next one. 24. Isn't 24 equal to 4 times 3 times 2? 4 times 3 times 2. And it happened to equal -6. And that's how I got c equals -1/4. Do you know anything else that's like that? That would be 4 times 3 times 2. Before that was 3 times 2. Well, these numbers are arising. If a simple way to write 24, instead of 4 times 3 times 2, I could write this 24 as 4 factorial. And so we have the notion of an nth degree Taylor polynomial. So the nth degree Taylor polynomial near x equal to a looks like this. I'll need p sub n of x. It will be nth degree. All right. So I need f of a, just like I was doing f of 1. Then I'll need f prime of a times x minus a. Then I'll need f double prime of a times x minus a squared. However, this is like the c that I was getting before. Right? This part was the c that I was getting, and so we had to divide by the coefficient in front of that. That was 2 factorial. And I keep going. I'll get f triple prime of a over 3 factorial times x minus a cubed. And this will go all the way until I get to the nth term. And then there we'll have f, the nth derivative, evaluated at a all over n factorial times x minus a to the n. So that's how we're going to do our polynomials. So let me use one now that uses all the terminology at once. Example 3. Compute the third degree Taylor polynomial to f of x equals 1 plus x to the negative 1/2 centered at a equals 0. So the way we're going to work this then is we're just going to keep track of the derivatives, and that will give us the numbers that we're looking for. Basically, here's my structure then. If my polynomial p sub 3 of x is going to look like f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared, and it's going to end when I get to the third derivative. And that'll be to the third power. But the a is 0, so this reduces to f of 0 plus f prime of 0 x plus f prime. Oh, don't forget these little factorial things that are underneath. F double prime of 0 all over 2 factorial times x squared, because x minus 0 is the same as x, so we have x squared plus f triple prime of 0 over 3 factorial times x cubed. And then we'll go about finding these numbers. Well, f of 0 equals, what was our original thing? F of 0 equals 1 plus 0 to the negative 1/2, which equals 1. So I have that spot taken care of. Now let me take the derivative of f of x. F prime of x equals, so we're going to take the negative 1/2 and bring it down. Negative 1/2, 1 plus x to the negative 3/2. So that f prime of 0 equals negative 1/2 times 1 plus 0 to the negative 3/2, which will equal negative 1/2. F double prime of x will equal, now I'll take the negative 3/2 and multiply it to the negative 1/2. I'll get 3/4, 1 plus x to the negative 5/2. And then when I plug in 0 into this, I'll just get 1 for this piece. So f double prime of 0 equals 3/4. And then f triple prime of x equals, I'll take the negative 5/2 and bring it down, and I'll get negative 15 over 8 times 1 plus x to the negative 7/2. And then I'll do f triple prime of 0 will equal, so this part is just 1, I'll get negative 15/8. So there we have my polynomial. P sub 3 of x equals, where's f of 0? That was 1. F prime of 0 was negative 1/2, so I get negative 1/2 times x. Well, it's just x because it's not x minus 0. I'm making it seem like I need an a, and I don't. Then we had a plus 3/4 x squared, and then we had negative 15 over 8 x cubed. What I want to do is take this and graph it against the original function to see how close they are together around a 0. Let me fix this before I forget. This is the 3/4, but you have to divide by 2 factorial. And this is still negative 15/8, but you have to divide by 3 factorial. Now, so we get then p sub 3 of x equals 1 minus 1/2 x. Now this will change this. 3/4 divided by 2 is 3/8. And then over here, 15/8 divided by 6 is 15 over 48, which is the same as 5 over 16. So let me circle this, and I will come back with a new graph. So as you can see, the approximation is even better. This guy right here was f of x, and this guy down here is p sub 3 of x. Let's, as I said before, I'm going to try at point 2. F of 0.2 was approximately 0.91287, and p sub 3 of 0.2 is approximately 0.9. So you can see that they're pretty close, almost to 3 decimal places. I guess if you were to round to 0.913, they'd be good to 3 decimal places. And so you can see the graphs are close to each other for a little range around x equal to 0. Compute p sub 3 of x for f of x equals arctangent of x. And so we know that p sub 3, do I have a region centered at a equals 1? So p3 of x is going to look something like this. It'll look like f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared, plus then f triple prime of 1 over 3 factorial times x minus 1 to the third. And let's go ahead and calculate all of these values. So I'll start with f of 1. That equals arctangent of 1, and that equals pi over 4. Now f prime of x equals 1 over 1 plus x squared. So f prime of 1 equals 1/2. F double prime of x equals, the derivative of this thing is not going to be a pleasant experience, but I'm going to think of it as 1 plus x squared to the negative 1. That way I'll get negative 1 times 1 plus x squared to the negative 2, but then take the derivative of what's inside, and you've got to attach a 2x. Then f double prime of 1 equals negative 1 times 1 plus 1 squared to the negative 2 times 2 times 1. And let's see what all that equals. I'll get negative 1 times 2 to the negative 2 times 2. That is negative 2 over 4, so this is going to equal negative 1/2. And then finally we're going to have f prime 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 of x, and I'm going to take it from here and use a product rule. I don't care about that negative sign, but if I think of this as a product, I will take the derivative of this piece first, and that'll equal negative 2 times 1 plus x squared to the negative 3. But then you got to take the derivative of the x squared to get 2x. And there was a 2x that was already there, so I'll call this 2x squared. And then when I take the derivative of the 2x part, that's just going to be 2. Now let me plug in 1. F triple prime of 1 is going to equal negative 2 times 1 plus 1 squared to the negative 3 times 2 times 1 squared minus 1 plus 1 squared to the negative 2 times 2. So let's see what all this ends up equaling. I'll have negative 2. This here will be 2 to the negative third, which is going to be 1 over 8. So I'll get 1 over 8 there. Then here I'll get a 4 here times 4. Well, that's nice. And then here I'll get, this will be 2 to the negative 2, so that would be 1/4. So I'll end up with the 2 and the 4 and the 8. That'll just give me negative 1 minus 1/2. So I'll get negative 3/2. So I have what I need. My p sub 3 of x equals, I'll rewrite what it's supposed to look like, and then underneath of it I'll put the answer. course, that's over 2 factorial, and that's over 3 factorial. So my f of 1, where did you go? F of 1 was pi over 4. F prime of 1 was 1/2. F double prime of 1 was negative 1/2. And don't forget to divide by 2 factorial. And then f triple prime of negative 1 was negative 3/2. And then I'm going to divide by 3 factorial times x minus 1 to the third. So let me do a little simplifying. This is no different than dividing by 2, so we'll get negative 1/4 times x minus 1 squared. And then negative 3/2 divided by 6 is, I think, negative 1/4. Let's graph the two of these things together and see what it looks like. And from the graph, it's hard to see it, but arctangent, this here is arctan of x. You can see, let me follow. I've tried to make the original function a little thinner than the derivatives. So when you look at this, here it goes down like this, comes down and goes like that. Our polynomial is a third degree polynomial. It actually comes in here and does this, and then comes down. So that's p sub 3. And you can see there's a region around x equal 1 where they're close to the same values. Let me throw in 1.1 and see how close they are to each other. So if I take a calculator and try to do tan inverse of 1.1, it'll give me approximately. So you can see that at least 2 decimal places in here, and they're working on the third place. Make your polynomial a little bit bigger and you will get more accuracy. So anyways, that's the gist of what we're going to be doing. The nth degree polynomial, or the, polynomial p sub n. A shorthand way to write it would be something like this. I would just do f to the n like this. And I wouldn't use n, I think I'll use k. Now, depending on where you're centering at, so this is the polynomial centered at a, don't forget to have k factorial times x minus a to the k, and k will equal 0 up to n. This will be p sub nx.